Now let's see how to plot two-dimensional arrays, sometimes called raster data, that represent either images or functions of two variables, also known as bivariate functions. The techniques developed are incredibly useful and will allow you to plot images and maps among other types of two-dimensional figures. Let's review some NumPy first. NumPy arrays resemble lists but are uniform in data type. They support vectorized computations or calculations over the entire array without having to write explicit loops. Square brackets can index arrays. For two-dimensional arrays, the syntax for indexing is open square bracket, index 0, index 1, close square bracket. A slice is a block of array entries. The principal notation for slicing uses colons. When slicing an array, the syntax is start, stop, stride. Remember, slices include the start index, but not the stop index. This is consistent with Python slicing. The stride tells us at which intervals to slice the array. For example, a stride of 2 will sample every other entry. Also, with negative indices or strides, we can count backwards from the end of the array. Now, here's a grayscale image of the famous Mona Lisa. Each pixel or picture element of the image has a numerical value. Any computerized black and white image is a numerical matrix with entries corresponding to pixel intensities. Conversely, any matrix corresponds to a grayscale image, the smallest entry being black and the largest entry being white. Similarly, any bivariate function, which is a function of two variables like this one, can be sampled on a discrete grid of xy pairs and the values stored in a matrix. This again makes an image. For instance, here we have an image constructed from a quadratic function of two variables. The darker values are near 0 and the lighter values are larger. The script meshgrids.py illustrates building the preceding image using NumPy's meshgrid function. The linspace command creates a 1D array of uniformly spaced values. The two 1D arrays from linspace, let's say u and v, can make two corresponding 2D arrays, let's say capital X and capital Y, using meshgrid. Meshgrid replicates the one-dimensional arrays u and v along different axes to make two-dimensional arrays x and y. The resulting 2D arrays have identical shape but are constant valued along different axes. The entries of x and y taken pairwise correspond to rectangular coordinates of a grid or mesh of points in the xy plane, hence the name meshgrid. The meshgrid represented by x and y makes evaluating a bivariate function on the grid easy. For instance, now we modify the script meshgrids.py from before to evaluate the function f of x and y equals x squared over 25 plus y squared over 4 on the mesh. Only the import statement at the top and the last 4 lines differ from before. The line assigning to z fills every entry of a 2D array. The following line prints the array, and the last 3 lines display the array as an image. The call to plt.set_cmap sets the color map to grayscale, and I'll explain this further in the next video. Here's the abbreviated screen output for displaying the matrix Z. And here is the resulting image from Matplotlib's pcolor. We'll learn more about pcolor a little bit later. As expected, the dark pixels are closer to 0 and the light pixels are larger in value. This image is created exactly as the preceding one, just with hundreds more samples in each direction on the mesh. There's a subtle orientation challenge in calling pcolor of Z, illustrated by the script orientation.py. Put simply, we write matrices differently by hand than pixels are drawn on the screen. Running this script shows the problem. When Z is printed, the values increase from 1 to 6 going left to right, and then from top to bottom from the top left corner. When pcolor plots pixels, values increase from 1 to 6, with values increasing from left to right, then vertically from bottom to top, starting from the bottom left corner. Be careful to get this orientation right when translating two-dimensional array into an image. It's time to get some practice building mesh grids and plotting arrays with pcolor. Let's look at a few different tools to visualize data arising from bivariate functions sampled on a two-dimensional array. For the moment, assume our matrix Z comes from evaluating a function on a mesh grid. Here we use the same function f of x and y as before. Remember, think of a plot Z as a grayscale image with dark pixels representing smaller values and light pixels representing larger values. If we create this 65 by 33 matrix Z and execute pcolor of Z, The result is a pseudo-color plot rather than a grayscale image. P-color stands for pseudo-color. We observe a couple of things. First, there are many colors rather than grayscale pixels. Second, the axes are spilling over, that is, there's white space on the sides. And third, the axes have large integers as labels rather than XY coordinates. So what happened? To understand the colors, let's display a color bar. We create a color bar with the command color bar. Now we see a vertical color bar to the right, illustrating a color map. A color map is a colored line associating numerical values with colors in some continuous way, just like a grayscale maps the interval from 0 to 1 to the spectrum from black to white. We can explicitly choose a number of built-in color maps with the CMap option. For instance, setting CMap equals gray forces a black to white color map. This results in a grayscale image. We can choose any of dozens of color maps, like autumn, which results in this figure with colors ranging from orange to yellow, representing increasing values. To fix the problem with empty space around the pseudo-color plot, use axis tight. This gets rid of the unattractive dead space. Notice the axis ticks are still integers determined by the dimensions of the matrix Z rather than the XY coordinates used to compute Z. We can fix this dead space and the axis tick numbering by calling pcolor with the mesh grid used to construct Z. That is, we execute pcolor X, Y, Z rather than just pcolor Z. The resulting figure has axis ticks determined by the arrays X and Y corresponding to the X and Y coordinates. These arguments are optional. When used, Matplotlib uses the mesh grid to label the axes. Pseudocolor plots tend to be blocky or pixelated. This may be appropriate for data that is inherently discontinuous. But we can use the function contour to make contour plots when the data varies continuously. We can see the contours are smooth curves along which the function represented by the data is inferred to be constant valued. Contour plots come from topographical maps where the contours are assumed to be points at the same height above sea level. We can specify the number of contours to draw, 30 in this case. This gives a plot with many more contours. We can also provide the mesh grid matrices X and Y as arguments, just as with pcolor. And again, the axis tick marks are determined by the mesh grid. Finally, the command contour F produces filled contour plots. The calling syntax has all the same options as contour. Okay, we've seen a lot of tools here. The API for Matplotlib includes many options you can read up on. For now, you can practice what you've learned so far in these exercises. Inferring distributions from data is a fundamental problem in data analysis. The points plotted here come from the automobile dataset, with weights of cars and maximum accelerations. When datasets consist of point clouds in 2 dimensions, visualizing the associated distribution closely requires tools similar to those seen so far. The fundamental tool for one-dimensional data is a histogram. That is, given a collection of realizations of a single random variable, we choose a set of intervals, or bins. Then we count the number of data points that lie in each bin, a process called binning. A histogram consists of the counts in each bin, which can be plotted as shown here. The Matplotlib function hist can be used to plot histograms, like the one just shown. We also have the option to choose the number of bins. The output of hist consists of an array of the histogram counts, an array of the bin edges, and a list of graphics objects representing the patches drawn. We'll see more powerful histogram plotting tools from the Seaborn library later. In one dimension, straight line segments are the only possible shape for bins in a histogram. But for data in 2 dimensions, bins can be more general shapes. We'll consider 2 kinds here, rectangles and hexagons. The most obvious strategy uses rectangular bins to build a 2D histogram. The Matplotlib function hist2d requires 2 vectors, x and y, specifying the coordinates of the data. We can specify the number of bins to use in the horizontal and vertical directions as a tuple. Notice we also use color bar to make the plot easier to interpret. The result resembles a pseudo-color plot because we can see the rectangular bins. The hexbin function constructs a similar 2-dimensional histogram using a hexagonal tiling for binning. Grid size is the number of hexagons to draw in the horizontal direction. It's a more sophisticated algorithm, so the optional parameters can be complicated to decipher. Here's the same bivariate probability distribution estimated using Hexbin. Notice the scaling on the vertical and horizontal axes are different, so the hexagons are not seen, in fact, as regular hexagons. Now it's your turn to build 2D histograms in the exercises.